My name is Cecilia, and I'm an engineer at Taiko. And currently, we're working on a base rolled up synchronous composability framework called Gwyneth. And in this talk, I'm also going to go over the generalization that we try to make it compatible for intercluster cross-chain calls. So what is synchronous composability? I would say a non-example of that is, for example, an intent-based protocol. We have RIP 7755 or ERC 7683, which a user will place her intent on chain A and hope for the best for a failure to fulfill her intent on chain B. And of course, everything is incentivized, but the reason why this being a non-example is the fact that she actually does not have any guarantee of whether the request will be fulfilled and what the result would be. It is atomic because this is just a one-step, one-shot request, so it's either success or fail. However, it's definitely not synchronous because message passing by nature is just not synchronous. Another non-example is, for example, you're doing a series of HTTP requests through your wallet. You're sending some through JSON RPC. You're trying to sell token on Optimism and buy meme coin on Taiko and then do something back on Optimism again. Through the network, that is also an example of non-atomicity and non-synchronicity and non-synchronous. However, an example of that will be something like a one-shot smart contract, like a entire atomic function call in a synchronous smart contract. In this case, this contract execute on Gwyneth REVM, and user is able to directly modify the status of chain from both OP and Gwyneth, right? You're swapping token on Optimism, and you're buying meme coin on Gwyneth, and then you're selling that thing back on Optimism. And in throughout the execution, you directly modify the database of both chain. So I would say in this case, we executed with entire atomicity and synchronicity because intrinsically everything is run in the same process. For an overview of the current status of cross-chain communication, we have intra-cluster communication where, for example, in OP superchain or Polygon's AG layer ecosystem, you have protocol-defined sequencing and deterministic cross-chain rules. However, it could be a little bit centralized because some of them are being run by protocol-owned shared sequencer. We also have intercluster communication. However, the consideration for that is, for example, settlement dependency. If chain A settle and chain B revert during while they're having interdependency between their states, then what do we do, right? Also, message facilitation. Who's actually gonna send the real message from Polygon to Optimism, and how do Polygon or Optimism read and write the message themselves? Should we do a shared sequencing protocol like Espresso? But the question is how much L2s are willing to give up the sequencing, right? And also we potentially can have a coordination protocol. A trusted third party can facilitate the message relay. However, rollup do have to opt in. So there is certain trust assumption. The example of that will be Espresso Circ, which is coordinated inter-rollup communication. And later on, I will present how we make ourselves compatible with Circ so that we're working closer towards some standard. So what we're trying to achieve at Gwyneth is to improve the status quo, right? So inside a Gwyneth cluster, we want atomic synchronous cross-chain call facilitated by the base builder. By saying a base builder, so this is an example, right? A base builder, a rollup is said to be base or L1 sequence when sequence is driven by the base L1 according to Justin. And in this example, what does that actually mean, right? The node that we're running actually have access to the mempool of both L1 and multiple L2s. While the node is sequencing for everything, this functions as a super builder that it can just pack the L2 transaction into a L2 block and form the rolled up proposal transaction and put it in the L1 block. And this L1 block will go get into the L1 through our regular beloved PBS pipeline. Yeah, so this is basically vanilla base rollup. And a bonus that I also try to present in our protocol is L1 composability. However, that's a little bit conditioned on how much we can lock on the L1 state. If we have execution pre-confirmation, we can do of the entire L1 block. We'll be able to do both L1 reads and L1 write. If we have some more limited pre-confirmation, we can only do L1 reads. For intra-cluster communication, we also want to achieve atomic synchronous cross-chain calls through some coordinated message relay. However, in order to make sure that it's secure, I'm also going to present a generalized multi-proof framework to ensure the consistency of inbound and outbound messages. So I'll start with booster rollup, the specific of how we're going to do atomic cross-chain call. For example, we have Gwyneth chain A and chain B. A base builder will sync for both chains for their transactions and states. The builder purchase sequencing right, or winning the block auction through regular PBS pipeline for both chain in this case, so that it has the exclusive state lock of the current state of chain A and B. And let's say at some point, chain A sees this call from the mempool that tried to call us into chain B. So this call will be consistent of code like that, like the X transfer code example that I'm showing. If we go through the execution of this code, the first, when we come into the context of this function execution, we are at chain A's execution environment. So we're accessing chain A's database that is on the left-hand side. So you're deducting balance of message.standard from chain A. And then we design this X call option precompile. While calling into this precompile, the node will perform a context switch that swap out the database and the state root from chain A to chain B. So by the time that we push the function call frame to the main function down below, we're already on chain B. We're already executing in chain B's environment. So this precompiles that Gwyneth REVM implement is how we achieve booster rollup, which lets you context switch between L1 and L2 DBs. And at the end of execution, we record the state diff and apply them back to A and B accordingly. And then this node will, of course, propose the block to both chain on L1 with its execution ticket. So there are some nuanced consideration when we're trying to achieve cross-chain execution. Because we use the base builder itself as the facilitator of message passing, we basically convert message passing into context switch. In a message passing scenario, transaction on A calls B needs to encode the call as call data and use some sort of relay or message coordinator to pass it over and await for the return. However, in our case, since everything is running in one process, transaction on L1 causing to B will directly modify B's state. And we will record the state diff and pass back the return. And A will continue the execution with this call data and return pair from B. So when individual nodes are syncing, let's say for B state, and that it doesn't care about A, then this is what it will see, right? Some B's transaction and some state diff that are that are being incurred from the fact that A calls into it, and also some call data and returns if itself calls into A. So when you're syncing the B node, you just have to process all of them, apply the state diff, and just take for granted whatever A returns back to you when you call A, and update your and reconstruct your final state. So the comparison between these two implementation is the fact that message passing is async in nature. There's no state law assumption when we're doing these back and forth. And also it's because it's not in the same building process. So we need to use proof in both cases actually to revoke calls that fails to ensure atomicity at settlement. However, context switch is synchronous with state lock. However, the state lock is being ensured by Gwyneth protocol. You have to have certain either execution ticket or just-in-time auction to ensure that these states are actually locked when you start building. Otherwise, whatever you build just cannot make it back onto the chain, right? A downside to that, to our state diff implementation, is we might lose some DA properties. So when chain B is syncing, if it only sees this like little triangle, the state diff over here, the actual call data, the actual call that incurs these states, that causes these state diff, is lost somewhere else. However, we can force the node to post the actual call for the B node to reconstruct, to re-execute and reconstruct the state. But I would say the state diff is one optimization, one DA optimization that we do so that we can batch transactions. Okay, what about L1 composability? That's what everyone's interested in. So like I just said, if we do have a super builder that builds for both L1s and L2, then we can basically do whatever with L1 block building, right? How do we do that? In vanilla PBS, the builder has to obtain the sequencing right for both A and B, and also somehow always win the PBS auction to build the L1 block. And that is very unrealistic for any layer 2. Like if I want to propose another block, I also have to win the L1 PBS auction. That's like super naive and not realistic. But what about we have pre-confirmation, right? With pre-confirmation, if we only have inclusion pre-confirmation, that means the L1 validator is promising the builder that I'm going to include your transaction somewhere in the L1 block. Then this builder for A and B can settle A and B somewhere in L1. However, since we don't have any view of the latest status of L1 chain, that means we cannot make any assumption of the current L1 state. So there's no read, no write. That basically means no L1 composability. But if we have top of the block pre-confirmation, that means the L1 validator can promise the builder that I'll place your transaction at the top of the L1 block, which I think in both API for pre-confirmation, they do have like a Boolean value to let the user specify if I want to be at the top of the block. So this should be realizable. Yeah, in that case, then the builder will make sure that A and B settles when the L1 begins. So it can actually read from the previous state, the L1 state from the previous L1 block. And then we have this one-time read that are guaranteed. And also you can write back to L1 when you're proposing your L2 blocks. So the state diff and all that stuff, at proposal, you write back to L1. The best case we can have, which is also a little bit unrealistic, is execution pre-confirmation for the entire L1 block space. So the L2 builder, if L2 builder can monopolize the whole L1 space, then that just basically means I can settle anywhere multiple times during the L1 execution. Yeah, and this also means full synchronous composability with L1. So full state locks across different chains is necessary to full composability, in my view. Okay, what about intercluster communication? Assuming we're trying to communicate with a non-base cluster X, where we don't have state locks and we cannot make any assumption. So the messaging has to be relayed by some third party because there's no super builder. In this case, we assume that we're collaborating with Espresso's cross-air rollup communication protocol, and in that protocol, they assume that there is a coordinator that facilitates the message relay, and they also mandate an inbox and outbox contract across the rollup that are communicating. So let's say Gwyneth chain calls a Espresso sequence chain with a bridging operation. We burn some token, and then we put that call in the outbox. So the Espresso coordinator, who's like syncing for both nodes, will either re-execute for the execute on behalf for the Espresso chain and write back the result back to Gwyneth. And at the same time, the coordinator will also send a RPC or send a transaction to the inbox to the Espresso chain to make sure the message is actually at the inbox and outbox of the Espresso sequence chain. Yeah, so towards the end, the view has to be consistent, and this Espresso coordinator who's also running on a TAE, hopefully it doesn't have mel behavior, everything should work in a happy case, right? So what are the considerations here? What can go wrong? First of all is message validation. We have to think about, do we need to also supply a proof with each message? What would the proof be like? Is it like a ZK proof for each small chunks of execution of each transaction? Or is it like a pre-confirmation of the fact that this message either gets included or the pre-confirmation of execution result? So these are two options. Or maybe we don't need any proof at all, right? But what about settlement validation? Because Gwyneth cannot assume any settlement result of this Espresso sequence chain. Maybe like if Gwyneth settle and Espresso revert, that would be terrible for us. That just basically means we burn some money, but like the money is not landed on the other chain. That just basically means like the money is stuck, right? To prevent that, I'll present a generalized proof framework that recursively verify the validity proofs of all chains on the next slide. And what about cross-chain clearance? There is another case where both chain mints and burns access with execution integrity. However, the number would not add up. Like Gwyneth will burn 10 tokens, however, Espresso will only mint 9 tokens. Like if you look, the validity proof of each chain will pass, but the accounting will be wrong. The balance sheet will not add up towards the end after proposal. So that's also another question, another problem that we have to resolve. So what we come up with is this idea of a glue proof. So the scenario is, right, there's certain message passing between two chains, and they propose, everything passes, the state rule landed. However, the clearance doesn't pass. Like the money in doesn't equals money out, right? How do we deal with that? So instead of directly letting the communicating chains propose to L1, we have a intermediate kind of ZK coprocessor, or like a glue prover, that they propose these transactions to the prover itself. So this is a real-time prover that simulate the verification. So what it does is it will, of course, run the make an L1 call to Espresso verifier. And the L1 call here, by the way, is the same L1 call that we use in the booster EVM. So I think like the reason why we do this is because we want to make sure that the prover itself is stateless. So we don't pull the verification contract from L1. Instead, we just like make a call to the L1 contract so that we also make sure that all these verification contracts are the latest for whatever chain that you're operating with. So yeah, we call this L1 verifier for all of the chain that are cross-communicating, make sure the execution validation is passed. And we also try to call the balance sheet, right? We run the numbers. If it's wrong, we atomically revoke all of the transaction, cross-chain communicating transaction that caused this number being wrong. So by the time where we actually propose for both chain, all these batches of malicious transaction would have been revoked. So this is basically delegated proposal, right? We're delegating the proposal of both chain with a real-time prover that glues across all different validity proof. The downside of that is, of course, all these chains that are being sequenced have to opt in for the glue prover and let us modify their state root, which can be security sensitive, right? So yeah, so towards the end, by the time we propose to L1, the money in should equal the money out, right? And also the validity proof should pass, and the L1's balance sheet checks out, and all of the settlement, both chains are settled at the same time. Since we're gluing the finalities, these are the consideration, right? Do we allow cross-block settlement? Because like we basically assume shared settlement across all of the chain. So I would say no in this design, because if A settles with the glue proof, however B hasn't made it to the L1 yet, then whatever that is being proven in the glue prover or the ZK coprocessor will be false, will be made up, right? If B actually doesn't land towards the end, and you're running all these message passing inside the glue TE prover, then basically what's being passed are fake, right? Are made up. But if we do have certain settlement schedule, then yes, you can submit a glue proof after every chain settles and revoke all of the transactions that are wrong, right? If for a period of time, if all these chains settle sequentially, and then you runs over a proof that proves across all of the chains, you can still do the revokes. However, that creates a lot of hurdle, because like assuming settlement is difficult. And I think like if chains want to communicate, the easiest way to do it is to assume shared settlement. What about the message, right? Like I said, like do we want a proof attached with different message, being attached to different message? I would say no, because as long as these atomic batch can be revoked, then we have guarantee that everything is secure. Even if any of these messages goes wrong, like the worst case scenario is that they do not happen, right? However, but if the user or the chains or the relayer needs certain security guarantee, I would say that the neutral relay need to generate these proof. And the last question is, we can also integrate pre-confirmation during the message passing, right? But with pre-confirmation, this idea, I have to credit this to Bo from Polymer's lab, because like he mentioned this idea during the sequencing week. And what the conclusion that we reach for this is actually very bizarre. I think if you have execution pre-confirmation across both chain in a very fast pace, you actually don't even need a glue proof, because for every step that you execute your transaction across chain, you already have the result. And these results are assuming pre-confirmation protocol is not broken, and assuming we have very high stake, very high collateral behind these execution pre-confirmation, then you can just take for granted the execution result when you're passing the cross-chain pre-confirmation with receipt. Yeah. So so this is, yeah, but in this case, it's only backed by crypto economic security. So theoretically, you can do cross-chain message passing with only crypto economic security. Yeah, but there's a lot more consideration needs to be made. So this brings to the end to my presentation. So I went over atomic synchronous cross-chain call facilitated by the base builder, and how we achieve L1 composability with state lock assumption. And finally, I presented a coordinated inter-cluster composability with the glue proof. So thank you very much.
Any questions? Oh, you got one here.
Thanks for the talk. I don't understand the difference between the glue proof and the ag layer.
It's very similar.
Okay, thank you.
Yes? Ian?
Yeah, thank you for the talk. I'm curious, so when you talk about in the context of shared base sequencing, you can get this L1 composability. If you had real-time proving so that you could have like intra-block settlement, would you also be able to compose in like a bidirectional way where not only can the L2 read and write with the L1, but the L1 would be able to read and write to the L2 within that same block?
Right, but that requires changes inside the L1 EVM, right? The reason why we can do a direct write from L2 to L1 is because basically this piece of code can run on Gwyneth. And then specifically there's this EVM.x call option that's basically a system call that swap between the DB. Well, if you want to do the same thing on L1, you basically need to run the same like Gwyneth EVM, which is not going to happen on L1, right?
Thank you. Yeah, that makes sense. Could you still do the reading part of the composability?
The reading part of composability.
So if you had like intra-block settlement of the L2 state at some intermediate state in that block, the rest of the L1 transactions could compose on top of that in like a read-only capacity?
Right. So if we have execution pre-confirmation, the entire building process of these like gray L1 transactions will be happening inside the same process. So when we go back to L2, you can access the latest L1 state, right? Yeah, and also like if we have top of the block pre-confirmation and prior to the very first blue transaction, you actually have the latest state of the previous L1 block that you can read from that with certainty that that state is fresh.
Got it. Thank you.
One last question on the first part of the talk. How do you compose this design with aggregation, like proof of aggregation? For example, very little people submit one block per block in L2s. They usually batch hundreds of blocks into aggregated proofs.
So that's possible if you do this, right? Well, like we try to force all L2 to practice share settlement, to settle in one block, because it's just easier. If we have like, you know, in this case, if we just prove like one single L1 block and just like prove whatever that settles inside, and hopefully if all L2 can share the settlement layer, then we can just keep batching, right? We can batch a bunch of proof while you just like run the L1 call to make sure that all of their verifications are correct. However, you can also have like a settlement schedule, which introduce much more hurdles, right? Your glue prover can run across multiple L1 block that make sure that, you know, like you just replay L1 transaction in a TE, in a stateless TE. Yeah, and in that case, you can cover a settlement window that allows different L2 blocks to settle. So theoretically, that is also possible. But yeah, there's going to be, something's going to break, I feel like.